in this next example, I'm going to be working example 5 from page 198. And I already have the picture drawn up here on the board that they have drawn in the book. So let me read the example to you. It says, Farmer John's tractor, traveling at 3 meters per second, pulls a rope attached to a bale of hay through a pulley. With dimensions indicated as in figure 7, which I have drawn on the board, how fast is the bale rising when the tractor is 5 meters from the bale? So, Farmer John has a tractor here, and he is driving it at 3 meters per second, directly out away from this bale of hay. Now, the bale of hay is right here, and it is rising right now. And what's going to be happening is, hopefully you can see, that this rope that is attached to the tractor, as that rope gets pulled, okay, that rope is going to have a direct relationship with the bale of hay because that rope is connected to the bale of hay through this pulley. So however fast this rope right here is moving, I'm going to label this R. I'm going to add that in there. However fast that rope is moving, that's how fast the bale of hay is going to be moving because it's connected directly to that rope. So the speed, the rate of change for the rope, will be directly equal to the change in the height of the bale of hay with respect to time. So these two things are going to be equal. The rope, the change in the rope, and the change in the height of the bale of hay. Now, another important fact for us to notice from the reading is that it's asking about how fast the bale is rising when the tractor is 5 meters from the bale of hay. So that means that if you went directly out from the bale of hay to the tractor, this distance would be 5 meters. In other words, this X up here is 5 meters because it is a distance directly out from the pulley to right above the tractor. So that distance X up at the top needs to be 5 meters. Now, this right here is labeled as 4.5 because if you notice, if this is 6 minus h right here, this red line is, and this blue line is h, then what that is indicating to us is that the entire distance from the top of the pulley to the ground would be 6, okay? And so if you took that entire distance 6 and you subtracted whatever distance you had on bottom, that would give you the distance on top. So that's where this 6 minus h and h is coming for. Now, if you pay attention to how the book does it, they do it in a way that's a little more complicated than what I'm going to do, and they use the fact that we have this 6 minus h and this h right here in a complicated way. But that simply means that this whole distance right here, all the way from the top of the pulley to the bottom, would be 6. But if you notice, this distance over here is labeled as 4.5. And the reason why it's labeled as 4.5 is because the rope is attached to the back of the tractor, and so the rope doesn't actually go all the way to the ground. It may be good to pull the tractor down a little bit, right? So this thing is attached to the back of the tractor, whereas the tractor is on the ground, the rope doesn't go all the way to the ground. The distance from the top of the pulley down to where the rope connects to the tractor is only 4.5 meters. So I'm going to call this distance y is 4.5 meters, okay? So y is 4.5 meters, x is 5 meters, and r is the length of the rope that we're talking about, okay? So hopefully you can see that we have a nice right triangle over here, and it's very convenient that the bale of hay is connected directly to this rope, and so its rate of change is going to be the exact same rate of change as the ropes. So we have this one small detail to deal with now. What exactly is the tractor affecting? Well, as the tractor moves out, the length of the rope is going to change. Well, that's what we're looking for. So we don't have that right now because as the tractor moves directly out in a straight line, the rope is not going to be affected directly by the tractor, right? The tractor is not the change in the rope. And also, it's not the change in the height. The height from the top of the pulley to where the rope is attached to the back of the tractor is going to constantly stay at 4.5 meters, which gives us a clue that dy dt is always going to be 0. So the height from the back of the tractor to where the pulley would match up is just going to be constantly 4.5. But you notice that the tractor is going directly out. And the other thing that we have that is going directly out is this distance right here, x. So this 3 meters per second going straight out is actually a change in our x value. It's a change in how far the tractor is from the bale of hay, and it's increasing by 3 meters per second. Okay? So those are some vital things to have connected here. The change in the rope is directly related to the change in the height of the bale of hay. The tractor going straight out is actually a change in our x value, and the change in the height from where the rope is attached to the back of the tractor to a line, straight out from the pulley is constantly going to be 4.5. Now, those three things, the 5, the 4.5, and the rope, are all going to be connected, hopefully you can tell, through the Pythagorean theorem. So y squared plus x squared should equal r squared, because r is the hypotenuse in this case. Well, before we get started, I hope you can see that we're going to need to know a distance for r, because when we take the derivative, there's going to be an r in this thing. So if we use the Pythagorean theorem and we plugged in 4.5 for y and 5 for x, we can find what r is before we get started with our actual derivative. So 4.5 squared plus 5 squared is 45.25. And then if we take the square root of that, we get that the length of the rope at this moment is 6.73 meters. That's important. That's something that we will need to use. Now, if you remember what I said from the last video, I said that we could plug in a constant before we actually take the derivative of the function if and only if the change of that variable with respect to time was equal to 0. So since dy dt is equal to 0, we can take 4.5 and plug it in before we go to take our derivative. So we'll plug in the 4.5, and now we're ready to take a derivative so that we can get our rates of change involved here. So 4.5 squared is just a constant. And when you take the derivative of a constant, you get 0. So that is going to go away. Plus, we have 2x dx dt equals 2r dr dt. And we can do our thing where we divide by 2 on both sides and cancel out the 2's. And so x times dx dt is going to be equal to r times dr dt. Now, we were given from the start that x equals 5, so I'm going to plug it in. And dx dt was 3, so I'm going to plug it in. We just found that r is 6.73, and we're looking for dr dt. So in order to wrap this thing up, all we need to do is divide by 6.73 on both sides. So if we do 5 times 3, that gives us 15 over 6.73 dr dt. So multiplying the 5 and the 3 gave me the 15 up top. And now we simply need to take 15 and divide it by 6.73. And we get 2.23 is equal to dr dt. And if you remember from earlier, we said that dr dt was directly related to the height of the bale's change. So the bale, dh dt, is rising at 2.23. And let's look at our units here. We were given our units in meters per second. So the change in the bale should also be expressed in meters per second.